Imagine a screen that requires a deep box behind it just to display an image. Now picture one thinner than your smartphone yet capable of the same clarity. This shift from bulky cathode ray tubes to modern flat panels represents a fundamental change in how we manipulate light and electrons, driven by distinct physical mechanisms rather than mere miniaturization. After that first surprise, we can slow down and trace the mechanism behind how TVS went from tubes to flat screens from the first physical step, so the effect stops feeling mysterious and starts feeling engineered. To understand how a television creates an image, we must first establish the vacuum tube environment where high voltage accelerates electrons from a cathode. Inside the sealed glass envelope, an electron gun fires a focused beam of negatively charged particles toward the front screen coated with phosphors. When these high-speed electrons strike specific points on the phosphor layer, their kinetic energy converts directly into light through atomic excitation. For instance, when electrons impact zinc sulfide doped with copper, they emit green photons at approximately 530 nanometers in wavelength. This precise interaction between particle motion and material response forms the fundamental basis of all CRT display technology. Pause 0.8 to generate an image on a cathode ray tube screen. We must precisely control the path of high-speed electrons traveling from the back of a device to the front phosphor coating. This steering is accomplished by a component called the deflection yoke, which consists of electromagnetic coils wrapped around the neck of the vacuum tube. When an electric current flows through these coils, it generates a magnetic field that exerts a force on the moving electrons according to the Lorentz force law. This physical principle dictates that a charged particle moving through a magnetic field experiences a perpendicular force that alters its trajectory without changing its speed. The challenge arises because we need to sweep this beam across the entire width of the screen, often at angles exceeding 45 degrees from the center axis. Achieving such wide deflection requires the electrons to travel a significant distance after leaving the magnetic field before they strike the display surface. Consider that if you attempt to bend the path too sharply near the exit, the beam will miss the screen entirely or create severe geometric distortion at the edges. Consequently, manufacturers must maintain a deep vacuum chamber extending several inches behind the glass faceplate to allow sufficient time and space for this magnetic steering to occur. This fundamental physical constraint is what gave traditional televisions their characteristic bulky profile compared to modern display technologies. Pause 0.8 to understand modern displays. We must first define liquid crystals as a distinct state of matter existing between solid and fluid phases. These molecules possess an ordered structure like solids, but flow freely like liquids when subjected to external forces. In the display panel, these elongated molecules are initially aligned in a specific twisted configuration by surface treatments on glass substrates. When no voltage is applied, this natural twist guides light through the pixel structure without obstruction. The mechanism activates when an electric potential difference is introduced across the conductive layers surrounding the crystal layer. This electrical field exerts torque on the polarizable molecules, causing them to rotate and align parallel to the field lines. Consider a concrete example where increasing voltage magnitude directly controls the degree of molecular twist reduction. At low voltages, partial rotation allows some light transmission while higher voltages fully untwist the structure, blocking passage. This precise manipulation transforms electrical signals into optical variations that form visible images on your screen. Understanding this molecular behavior provides the foundation for how polarization filters subsequently modulate transmitted light intensity. Pause 0.8 to understand how flat screens create images without glowing themselves. We must examine the role of polarization filters. Liquid crystals do not emit light. Instead, they act as valves that control whether backlight passes through or is blocked. Imagine two polarizing filters placed at right angles to each other, like a vertical gate followed by a horizontal one. In their natural state, liquid crystals twist incoming light so it can pass through both filters, creating a bright pixel. When voltage is applied, the crystals align straight and stop twisting the light, causing it to be blocked by the second filter. This mechanism creates contrast by selectively allowing or preventing light from reaching your eyes at each pixel location. Without this modulation system, we would see only uniform brightness across the entire screen surface. This reliance on external illumination leads us directly into examining how modern displays generate that essential backlight source. Pause 0.8 The transition from bulky cathode ray tubes to flat screens required a fundamental shift in how light is generated behind the liquid crystal layer. Early LCDs relied on cold cathode fluorescent lamps, which function through gas discharge physics, where high voltage excites mercury vapor inside a sealed glass tube. This process creates ultraviolet photons that strike a phosphor coating to emit visible white light, similar to traditional fluorescent bulbs, but scaled for display integration. In contrast, modern LED backlights utilize semiconductor recombination within diode junctions, where electron hole pairs release energy as photons upon electrical excitation. The geometric difference is stark. CCFL systems require long curved tubes positioned behind the panel or along edges, whereas LEDs are discrete surface-mounted components arranged in precise arrays. This architectural change enables edgelit configurations that reduce thickness significantly compared to direct-lit setups, where hundreds of individual diodes illuminate the entire screen area uniformly. While both technologies serve the same purpose of providing uniform illumination for liquid crystals, the LED approach offers superior energy efficiency and eliminates mercury content entirely. Pause 0.8 A plasma display panel relies on microscopic cells sealed within a glass substrate, each containing a precise mixture of noble gases like xenon and neon under controlled pressure. When an electrical voltage is applied across electrodes surrounding these cells, the gas undergoes ionization once it reaches a specific threshold potential. This process strips electrons from atoms to create a conductive plasma state that emits ultraviolet photons through electron excitation and subsequent relaxation. Unlike traditional fluorescent lamps, where mercury vapor serves as the primary emitter, plasma screens utilize noble gases to generate high-energy ultraviolet radiation without toxic byproducts. The emitted ultraviolet light strikes phosphor coatings lining each cell wall, causing electrons within those materials to jump energy levels before releasing visible photons in red, green, or blue wavelengths. This conversion mechanism allows individual subpixels to produce distinct colors to controlled electrical discharge patterns rather than continuous backlighting systems. Understanding this gas discharge physics provides the foundation for examining how modern displays have evolved toward organic electroluminescence. Pause 0.8 We begin by defining the layered structure of anode, cathode, and emissive organic compounds that form the core of this technology. Unlike plasma screens where ionized gas excites phosphors indirectly, OLED panels utilize organic molecules to emit light directly when current passes through them. The mechanism involves electrons moving from the cathode and holes moving from the anode toward a central emissive layer. When these charge carriers meet within the organic material, they undergo recombination processes that generate photons directly from excited molecules. This process is analogous to how individual pixels in a digital display can emit light independently without requiring a common backlight source. Each pixel operates as its own light source, allowing for perfect blacks and infinite contrast ratios compared to traditional LCD technology. Pause 0.8 We trace the evolution from electron beams striking phosphors to electric fields rotating crystals and finally direct emission from organic layers. Each transition solved specific physical limitations of its predecessor through distinct mechanisms.